In this video, we're going to solve the initial value problem given by this differential equation, satisfying the value at 0 is equal to pi over 2. The first thing that we're going to do is look at the expression and see that on one side I have the derivative, dy dx. On the right side I have what appears to be a complicated rational expression. I can factor this expression, in fact the numerator factors. I can factor out that x that appears in both of the terms, so let's do that first. So dy dx is 2x times y squared plus 4, and I still have x squared plus 4. Now the fact that I was able to factor it into two expressions, one only involving x and one only involving y, tells me that this is a separable differential equation. That means we should separate the variables and then integrate both sides. In this case, I need to get the part with the y squared plus 4, over to the side with the dy. So we're going to divide both sides by y squared plus 4. On the right side I have just the expression involving x. And then next what we'll need to do is take the differential dx and move that over to the other side, and we'll have separated the variables. So let's do that next. Next we'll integrate both sides. Notice the differential tells you the variable of integration. In this case I'll be integrating with respect to y on the left and with respect to x on the right. The left hand side looks like an arctangent form, and in fact after adjusting for the constant of 4 here and using the arctangent formula, we'll have 1/2 arctangent of y over 2. The right hand side will need a substitution of x squared plus 4. Its derivative is 2x. So du dx, the differential du is 2x dx, which is exactly what appears in the integral here, 2x dx. So we'll be able to make that substitution very cleanly. We'll have du over u. And then when we integrate 1 over u, we get the natural log of u. We'll put the constant of integration on this side. And back substitute, we'll get the natural log of x squared plus 4. So what we have here is arctangent of y over 2. I'll double it. There's the 1/2 here, so I'll double both sides. And that's 2 times the log of x squared plus 4. And then 2 times the constant of integration. We'll just call that new twice the constant c1. So c1 is just 2 times c. Notice that that 2 in front can be raised to an exponent using the properties of logarithms, so that the 2 times the log becomes log of that expression squared. I don't need the absolute values anymore because it will be positive. And what we have here is implicitly given general solutions to the differential equation. It's implicit because I have the y not explicitly solved for. It's trapped right now inside this arctangent function. Let's use the initial value, y of 0 is equal to pi over 2, to find what c1 should be. So y is equal to pi over 2 when x is 0. Let's plug those values in for y and x. When I plug it in for y, I have to take half of it here, so I'll have pi over 4, not pi over 2. And then when I plug in 0, I'll be taking log of 4 squared, so log of 16 plus this constant that we're trying to find. Arctangent of pi over 4 is equal to 1. So c1 is equal to 1 minus the log of 16. The log of 16 is just the log of 16, some number. And that explicitly gives us the constant of integration that we're looking for. So now we can go back and plug that into our equation. Arctan of y over 2 is log of that plus this constant. And at this point we've found the unique solution to the initial value problem. Notice that it's given implicitly. We can find the explicit solution by taking the tangent of both sides. So y over 2 is the tangent of all that appears on the right side. And I've highlighted the parentheses here. Make sure you respect the constant term as well. That's inside the tangent, not outside the tangent function. And then y over 2 is not exactly y, so let's double everything, and y is 2 times the tangent of this complicated expression in the inside. That is the explicit solution to the initial value problem.